This is the classic joke. If anybody's heard anything about fusion, it's the perfect energy source that's 30 years away and will always be 30 years away. I hate that joke so much. I hate it so much, I'm dedicating my life to eliminating that joke from the English language.
Welcome back to Today I Learned Climate, the podcast where you learn about climate change from real scientists and experts. I'm your host, Laur Hesse Fisher, with the MIT Environmental Solutions Initiative. Today's episode concludes our series on energy and climate in partnership with the MIT Energy Initiative. Our guest today is an expert on a technology that could completely change our global energy system, but so far hasn't powered a single light bulb.
My name is Dennis Whyte, Whyte with a Y, and I'm a professor here at MIT, and I'm also the director of the Plasma Science and Fusion Center of MIT.
Professor Whyte studies fusion energy, which is the process that our stars use to generate so much heat and light.
Stars, by the way, in our own sun is just a big ball of hydrogen. Most of the universe is hydrogen. So hydrogen is the simplest and most abundant element by far in the universe. At the center of a sun and a star, it becomes hot enough and there's enough pressure that the hydrogen that wants to stay hydrogen is forced to get close enough to another hydrogen, and they fuse and they produce helium. And when that happens, it releases staggering amounts of energy. It's 20 to 100 million times more energy released per particle than you can ever get out of a chemical reaction.
So you're saying that the kind of energy that we can produce right now by burning coal and burning natural gas is just absolutely nothing like the kind of energy that you can produce with fusion.
That's right. What we're after is bringing the power of the stars, which is essentially inexhaustible, down to Earth to mankind.
Okay, but if fusion naturally happens inside of a star, then what does it look like here on Earth?
So what we make is, it's actually a rather modest looking object that's got some high tech inside of it, but what we're making is a magnetic cage. It looks like a big piece of steel, kind of, but it's not that large. It's about the size of like a coat closet. So first thing that we do, we get all the air out. We build a steel chamber and we evacuate every particle. So it's basically a vacuum like outer space. Then we put in a little bit of the fuel, the hydrogen, but teeny amounts. And then we zap it with some heat and get it hot really quickly. The challenge of fusion is that fusion happens in one place, in the center of stars, because it's the one place that can get hot enough to make fusion happen. So at its heart is about getting the fuel, the hydrogen, hot enough.
How hot does it need to get?
So the center of our sun is about 15 million degrees Celsius.
And what is, in Fahrenheit?
No, we never use Fahrenheit. It's about like 25 to 30 million Fahrenheit. Sorry, I never think in Fahrenheit. So it turns out to make it work on Earth, it has to be at about 100 million degrees. Okay.
That's inconceivable.
Yes. Most people just sort of have a guffaw moment. Like what? How can that be possible? We as humans have almost no intuition about what something feels like at that, because we can literally never touch it. So we're used to thinking about temperature, right? But over ice is cold, lukewarm water, you touch an oven, it's really hot. This is an incredibly small range of temperature.
Right. Things can get a lot hotter and a lot colder than what we experience in our daily lives. When you crank up the temperature to thousands or millions of degrees, something fascinating starts to happen.
Ice, what happens when you heat it up? It melts, it becomes a liquid. What happens if you then put that liquid on your stove and get it hotter? It becomes steam, it becomes a gas. So it turns out, though, if you take that gas and that steam and you keep making it hotter, actually at about 5,000 degrees, something really fundamental changes in matter. It becomes a different phase of matter again. It becomes something called a plasma.
You might have seen pictures of plasma on Earth, lava from volcanoes. Lightning also is actually plasma. You may also have seen close-up pictures of the sun. The tumultuous surface and solar flares are also examples of plasma. And that's what's inside Professor Whyte's fusion chamber.
Something at 100 million degrees sounds dangerous, but it's actually the opposite. It's because it's, to use a technical term, it's so far out of equilibrium with the rest of the Earth, blowing on it actually turns it off. My breath is at room temperature, and there's more particles in my lungs than there are in the fusion. The listeners can't see this, but you'll see what I'm doing. like blowing out like a birthday candle. That would extinguish the fusion immediately inside of this. So it turns out that's actually the objective that we have achieved quite routinely, is the 100 million.
Right, actually getting the temperature to 100 million degrees, which is still inconceivable to me, isn't actually the biggest challenge of producing energy from fusion. It's about getting all the conditions in place to keep the fusion reactions going.
We need to supply heat to actually get it hot. So the equivalent is thinking like of a match. You put a bonfire together, here's a match. That's the initial source of heat. But then the bonfire lets itself keep going. We've never made the bonfire. Like we've lit the match, we've gotten the wood hot, we've studied it, but it never took off. And what that requires is actually that you're making so much fusion energy that it's keeping itself hot primarily, and you're making a lot more energy from the fusion than the heat that's required to make it hot.
Yeah, and that's how stars work. They're made of hydrogen and are able to keep fusing together hydrogen atoms into helium, making a chain reaction of fusions that's able to sustain itself. And so that's the challenge here on Earth, keeping the chain reactions running long enough that it generates more energy than what we're putting into it to get it that hot in the first place. But the prototype that Professor Whyte works with here at MIT is one of the most advanced examples of fusion energy here on Earth, and he thinks he's getting close to having this happen.
So how does this look like in the real world then? If you just draw a box around the exotic part, it just looks like a heat source.
So then is it boil the water and produce steam and turn a turbine?
So you that's actually one of the things you can do with it. That's actually, we think we can actually be much more efficient than that, because one of the features of fusion is it can make like staggeringly what we call very high quality heat. We tend to keep thinking about decarbonization and the climate crisis around making electricity. Electricity is like at most a quarter of the problem. Like decarbonizing long-range transportation, industrial heat processing, refining fuels, concrete. These things are all have intense heat requirements. So what fusion has at its heart is that it doesn't just plug into the electrical infrastructure, it plugs into our energy infrastructure overall.
We've mostly focused on electricity in this series, but if you're making concrete or steel, what you need is a ton of raw heat. Way more heat than electricity could provide. Right now, those kinds of factories use fossil fuels for that intense heat. But fusion could deliver that. Fusion power could also be dispatchable, which means it can be turned on and off exactly when we need it, unlike other forms of clean energy like wind and solar power.
It's an on-demand energy source. You can control the amount of fuel and the power output on the timescales of like seconds. You can turn it off in a fraction of a second.
And then there's the sheer amount of energy that fusion can deliver. In fact, it is so much energy that Professor Whyte actually sees it as a challenge of getting the first fusion power plant out in the real world.
One of its limitations is that it has a minimum level of output of power to make the star work. The minimum unit is probably like 50, 100 million watts of power, which is a lot of power. Like in the energy market, that power is like a small city. So we'd have to build it at an enormous scale to get the very first one going.
This is all why people are so excited about the potential of fusion energy.
I don't think it's an exaggeration to say that economic fusion energy changes the world. It changes humanity's relationship to energy and how we use energy. It can be deployed into many of the present energy systems and infrastructures, and it can be deployed anywhere on the planet in principle, because you don't need particular access to a particular kind of fuel.
All right, let's come back down to earth for a second. Affordable fusion energy doesn't exist yet, and even Professor Whyte can't promise that it ever will. So why spend so much time talking about it? Well, one of our main messages in this energy series is that no one energy source can get us to a carbon-free system on its own. We've heard scientists from all kinds of backgrounds tell us that we need many strategies together. Wind and solar, along with energy storage and new power lines, energy efficiency with renewables, older technologies like nuclear, and young ones like carbon capture and storage. The potential of fusion shows us how much we could gain from also making investments in totally new energy technologies. And it's not just fusion. There are growing energy sources that we haven't had time to dig into, like hydrogen power, advanced biofuels, concentrated solar power, which is totally different from the solar photovoltaics that we covered in our episode on wind and solar. All of these together could fill huge gaps in our ability to decarbonize our whole energy system, from electricity to transportation to the heat needed to make things like concrete and steel.
Decarbonizing our energy use is probably the hardest thing humanity will ever have to try. Changing how you make and interact with energy is at the heart of everything that we do. It's our entire way of life. We need all hands on deck on all the clean energy sources about getting there. And I really want to make sure fusion has a real fighting chance of being one of those.
For more on fusion, check out the MIT Energy Initiative's podcast interview with Professor Whyte, where he speaks more about commercializing fusion energy. We'll also have other resources, including a guide for educators to use this podcast in the classroom, on our website, tilclimate.mit.edu. Thank you for tuning in to Today I Learned Climate, brought to you by the MIT Environmental Solutions Initiative. This was our last official episode in our second season, which we produced in collaboration with the MIT Energy Initiative. I say that it's our last official episode because we may have a bonus episode or two up our sleeve, so just a heads up. We're now preparing for season 3, so if there's a topic that you'd like us to cover, send us a tweet at TILClimate or email us at tilclimate@mit.edu. I want to recognize our team, those who worked on our first 2 seasons, our student production assistants, Ruby Winsell, Cecilia Ballone, Daria Gutler, Olivia Burrick, and Skyler Jones, our graduate student writers, Jessie Hendricks and Rachel Fritz, Aaron Krol, who did our show artwork and is a contributing writer, Blue Dot Sessions created our music, the fabulous David Lishansky, our audio editor and producer. I'm your host, Laur Hesse Fisher. I want to thank Professor Dennis Whyte and all our experts for speaking with us for this season, and thank you for listening.